So in this video we're going to examine RC circuits. These are circuits that have at least one resistor and one capacitor. And they can seem kind of intimidating at first until we get used to them. So let's take a look. First we're going to look at an easy example, then we're going to look at a difficult example. So here's our easy example. We have a battery that is in series with a resistor and the resistor up here and a capacitor down here. And the problem, which is from problem 44 in Giancoli's book in chapter 26, which is another book that's kind of equivalent to our book, we have a total resistance that's actually given, this resistor value R, and the battery value, and we don't know the capacitance, and we don't know the time that it takes for the voltage to do such and such, so to speak. But we are given the time constant. So let's see how we would examine this from first principles. In other words, let's pretend that we did not already know a formula for the time constant. So here we go. We're going to use Kirchhoff's loop rule for this circuit. Remember, we just have a battery and then a capacitor, then a resistor. And we're going to pretend that the resistor was first. So we have the battery's EMF, the battery power, so to speak, or at least the voltage of the battery, assuming that it's an ideal battery, minus IR. In other words, that's an Ohm's law. We have a voltage drop going across that resistor, and also minus that voltage drop that would occur going across that capacitor, because we do go from positive to negative going across that capacitor. So we can write the current as dq dt, because that is the derivative with respect to time of the charge that is leaving the battery, so to speak. But whatever charge is leaving the battery is accumulating on the capacitor. So we have that simply becoming a positive, or actually it remains a negative dq dt, because there's this current that's going through the resistor at that time. So that's what we have at this point. So now we get an equation that is going to turn into a first order differential equation. In other words, we're going to move everything that has a time onto one side of the equation and everything that has a q on the other side of the equation. And essentially we're going to realize that everything that we have right here is all q's. Everything that we have right here is all times. This is the technique called separation of variables for a first-order linear differential equation. It doesn't work for all first-order linear differential equations. In other words, if there was some function of time over here, we'd probably have to use a different strategy in general, unless it turned out to be set up in just an easy way. But in this case, it is an easy way, and we can separate our variables like this. And the reason that technique is important is because now we can simply slap an integral sign on everything and realize that as this capacitor ends up charging, it's going to go from a charge of 0 up to a charge of positive q over a time from 0 to t. And we don't know what that positive q is, we don't know what that t is, but the point is, if you tell me what the t is, I can tell you what that positive q is. Also notice that I changed my variable names to prime names because I didn't want to use the same symbol for the variable as the actual fixed item right here. In other words, our integration bounds. And in general, that's a good technique. Unfortunately, it's relatively rarely practiced, but it should be practiced, so I'm practicing it here. So the right side of this equation is very easy to integrate. The left side of this equation, it's not too bad to integrate once we do a variable substitution. In other words, if we could replace this denominator by something else, we'd basically have a natural logarithm right here. So that's actually exactly what we're going to do. We're going to define that denominator as u and recognize that the derivative with respect to u is just a negative the derivative with respect to q prime. So everywhere we see a c e minus q prime, we're going to replace that with a u, and everywhere we see a negative dq prime, we're going to replace that with a du. Well, we don't have a negative dq prime, but we do have a positive dq prime, so we're just going to replace that with a negative du. See, there's that negative sign right there. And on the right side of the equation that we had before, we simply integrate this with respect to time. That just gives us a t, and plugging in the bounds of that, or it's going to give us t prime, plugging in the bounds of that, we just end up getting a t over rc left over. That 1 over rc was factored out at the beginning. So what about the left side of this? Well, you can integrate this. This is a natural log of the absolute value of u. And u is always positive in this case, so we don't even care about that absolute value. And I'm just going to plug that u back in there. And now we're going to plug in our q and our 0. And when we do that, we get a natural log of 1 minus q over EC, where E is the EMF of the battery voltage, so to speak. And we got that by recognizing that a subtraction of logarithms is a logarithm of the quotient of the things. So there we go. There's our equation. So now we can exponentiate both sides and get this result. And then we get, after a little bit of algebra, that q is equal to this as a function of time. Now, we don't care about q. We care about what's happening with the current. In fact, what we really care about is what's happening with the voltage. So what we're going to do is we're going to take a derivative with respect to time of that equation for q. That's going to give us the current as a function of time. There we go. In other words, I'm just going to distribute this CE through. That's going to be a constant right there. The derivative of that's going to be 0. It also distributes through to this other term right here. So we're really just taking the derivative of this other term right here with the CE in there. And that's just that term itself because we're dealing with an exponential, but by the chain rule we need to take the derivative of that exponent, which is a minus 1 over RC. So that allows our negatives to cancel. It also allows our C's to cancel. And this E over R, you recognize that? That's something that we are going to be getting familiar with. That E is V and that IR, that's looking kind of familiar there. So, well, since V is equal to IR, we can just multiply both sides by R, and now we get V as a function of time. And there it is. So that's the equation that we're dealing with at this point. And what do we have here? We have V as a function of time, and we also have an expression for that time constant, because that time constant, by definition, is the time it takes for whatever we're dealing with to reduce to 1 over E of its original value. That's how you talk about time constants when you're dealing with exponential equations. It works for things like radioactive decay and stuff like that as well. So time constant is RC. So first, they ask us to calculate the total capacitance. Well, they give us the time constant. They also give us R, so now it's just kiddie algebra. And we get a capacitance of 1.6 times 10 to the minus 9 farads, also called 1.6 nanofarads. So there's our answer. What about the time it takes for the voltage across the resistor to reach 16 volts after the switch is closed? Well, we have our time constant, we have our voltage, and we have our EMF of 24 volts. So there's our equation that we just derived for V. We're going to take the natural log of both sides of that, and after a little bit of algebra, we get that the time is going to be equal to the time constant times the natural log of the EMF divided by V. So again, just using some rules of logarithms is how we got that. So now we're ready to plug in some numbers, and after we do that, we get 0.973 times 10 to the minus 5th seconds, which is the same thing as 9.73 microseconds. Now let's take a look at a harder problem. Here we have a battery, which we're just saying that it's throughout this entire area, and we have some resistors here, and we have some capacitors here. And there's also a switch that has the ability to connect these sides of the circuit. So we have a number of different problems here. First, what's the potential at point A when the switch is open? That turns out to be easy enough to figure out. How about at point B when the switch is open? That's also relatively easy to figure out. And then when the switch is closed, what is the final potential at point B? That turns out to be, again, easy to figure out. And then how much charge flows through the switch after it is closed. That's a little more difficult to figure out, but it's something that we can do. The hard part is part E. When the switch is closed, what is the effective time constant, or constants, for the capacitors that are charging? And that's going to take a while to figure out. So let's see how this goes so far. So the potential at switch at point A when the switch is open. In other words, we don't have anything special really happening. Yeah, the capacitors are charging, but we can just do a little loop rule here, and it turns out not to be too difficult to deal with. So we're going to use Kirchhoff's loop rule and realize that the equivalent resistance here is 13.2 ohms. In other words, we write our givens here and say that this is R1, that's R2. We're actually going to rename these things later, but for now, when we're just dealing with this in parts, it's easier just to call this 1 and 2 and this C1 and C2. So equivalent resistance is 13.2 ohms, and since the EMF is 24 volts, that means that we're going to get a current of 1.818 amps coming out of the battery. So it's going to go into charging the capacitors, but it's also going to go through these resistors as well. So it's doing two things simultaneously. When the switch is open, we simply have a almost pure parallel type of thing. The capacitor system is in parallel with the resistor system. So things are happening independently at this point. So now, to figure out the potential at point A, we realize that, well, by the loop rule, we're going to start off with 24 volts, our EMF, and we're going to go down a waterfall here, an IR right here. We're going to lose that, so that 24 volts minus this IR is going to be the potential at A. So when we shove those numbers in, we get the potential at A is 8 volts. If you think about it, that shouldn't be surprising. That's 1/3 of our original battery potential. This resistor has twice as much resistance as this other resistor, so you should expect that you would lose 2/3 of your battery's power going across the resistor that's twice as strong as the other resistor that's in series. In other words, this waterfall is twice as high as this waterfall. So you go down 2/3 of the way. So by the time you go down 2/3 of the way, you are 1/3 of the way up. So that part, not too hard. How about the potential at point B when the switch is open? Well, to do this, we need to figure out what sort of charge is on these capacitors, and that's going to allow us to figure out the voltage drop across each capacitor. In particular, what we care about is the voltage drop across this capacitor right here, the first one, because then we just do a 24 volt minus that voltage drop, ends up being the potential at B, similar to how we got the potential at A. So to figure out the equivalent capacitance, remember capacitors in series. To figure out that equivalent capacitance, you need to add the inverses and invert the result. So adding the inverses, here I noticed that I could get a common denominator here by multiplying this whole thing by 0.75 over 0.75. So did that sneaky little thing, so we get a 1.75 over 0.36 microfarads is equal to the inverse of our capacitance. So inverting that result to get our capacitance, you get 0.2057 microfarads. Nothing really special about that number. That's just the equivalent capacitance. So now that we know the equivalent capacitance, we can figure out the charge really the charge between this top plate right here and this bottom plate right here. And that's going to be the charge on each capacitor, because there isn't going to be any charge that's going to be allowed to go in here. There's nowhere for it to escape, in other words. So there's our equivalent capacitance. And since the difference in voltage for the whole circuit is 24 volts, that's going to be also the voltage drop across the two capacitors. That's going to allow us to figure out the charge on each capacitor. So I'm not even going to bother calculating that at this point. I don't need to. In other words, my potential at point B is equal to my battery's voltage minus the voltage drop across that first capacitor. What is that? Well, that's the charge on that divided by its capacitance. Well, I already have an expression for the charge on that. That's the equivalent capacitance times the battery voltage. So I plug in a CEQ times E right here, and I can factor out that script E. So that's exactly what I do. And we already know what the equivalent capacitance is. We know what C1 is. We're ready to plug in and be done with part B. So when we do that, we get 14 volts. So now it's time to move on to part C. When the switch is closed, what's the final potential at point B? That's actually the easiest part, because when the switch is closed, if you go back to that switch on the previous slide, you realize that that's a wire connecting points A and B. A wire is a conductor. A conductor is an equipotential surface. Well, we know what the potential is at point A because of Kirchhoff's loop rule. That's easy enough. That current, after it's been closed for a while, it's going to be in equilibrium, so there will be no current flowing into the capacitors anymore, so the only current is going to be going through the resistors. That's what we already had in part A. So that potential is going to be 8 volts. Now, what about part D? How much charge flows through the switch after it is closed? This is the first time we're going to deal with a little bit of difficulty here. In fact, you can already tell the font's getting smaller. So, to figure this out, we're going to recognize that before the switch is closed, the requirement was that the potential at point B was such that the two capacitors had the same charge. But after it's closed, it's going to be such that you have the same potential between points A and B. So, that's going to be a change. That means that there's going to be some charge flowing through this switch after it closes, because there's a change in potential. And we don't really have a change here, so that's something that we're going to be dealing with. So after the switch is closed, delta V on each capacitor will match that of its respective resistor. In other words, after the switch is closed, this capacitor is going to be in parallel with this resistor, which means that the voltage drop across this resistor will be the same as the potential difference across the plates of this capacitor. Likewise for this capacitor compared with this resistor. We're going to use that here. So, because of the fact that there's going to be now a charge imbalance on the two plates, in other words, there will be a different amount of charge on this plate because there's a different voltage drop, and different voltage drop here, and it's not the same voltage drop that it was before. Now there's a charge imbalance, which means that there's going to be effectively some charge on this wire right here. That's okay because it's being supplied by a current that's coming through the switch. At least it has been supplied at the end of some time. So let's see how we're going to attack this. So we're going to analyze the charge on each capacitor after the switch is thrown and the circuit comes to equilibrium. So the voltage drop across capacitor 1 is the same as the voltage drop across this resistor, which was 16 volts. In other words, 8.8 ohms times that current that we had calculated before. And again, just kind of by symmetry, you lose 2/3 of it here and 1/3 of it here. So 16 volts there, well, that's got to be the same as the voltage difference between the positive plate and the negative plate right there. It's 16 volts. So that tells us the charge that's there, 7.68 microcoulombs. Now we do the same thing for the lower capacitor right here. So that potential difference is 8 volts because there's a voltage drop of 8 volts across this resistor, and this are now in parallel. Because again, A and B is an equipotential surface. So now, plugging those numbers in, we get that the charge on this capacitor is 2.88 microcoulombs. Again, that's different now because here we have this connection here. These resistors are changing things up. We have this wire. This wire is an equipotential surface, which means that the potential difference between here and here has got to be the same. So after everything comes to equilibrium, we have 2.88 microcoulombs here, 7.68 microcoulombs here. Well, what does that mean? That means that there is now a net charge on this wire because, let's see, we have positive 7.68 microcoulombs on this top plate right here. We have negative 7.68 microcoulombs on this bottom plate right here. Well, we also have positive 2.88 microcoulombs on this top plate right here and negative 2.88 microcoulombs on this bottom plate right here. Overall, with negative 7.68 microcoulombs right there and positive 2.88 microcoulombs right there, this wire, which contains point B now, has a negative charge now. It used to have a total charge of 0. Now it has a total charge of this positive charge minus the magnitude of this negative charge, which is negative 4.8 microcoulombs. This wire went from 0 coulombs to negative 4.8 microcoulombs, which means that 4.8 microcoulombs of charge ended up going from B to A through the switch. So it had been 0, now it's negative, so 4.8 microcoulombs flowed from B to A after the switch was thrown. So that's part D. Now let's move on to part E, the hardest part. Bear with me, this part has 6 slides, and some of the slides have kind of small font. So here we go. When the switch is closed, what is the time constant for charging the capacitors after the 24-volt battery, so to speak, is applied? In other words, we're going to have currents changing as a function of time. Well, now we need to relabel some things. We're going to call this resistor R1 right here. We're going to say that a current of I1 flows through it. We're going to call this capacitor C3, and this lower resistor, by the way, here was R2. A current of I2 goes through it. This capacitor is C3. Current I3 goes through it. This capacitor here is C4. Current I4 goes through that. So that's encapsulated with these givens and just this reminder of what we're dealing with here and how we're denoting our variables. So what we need to do is we're going to use the Kirchhoff's loop rule a few times, as well as the junction rule a couple of times. So by the loop rule, just going along the outer loop, we first have our battery voltage. And remember, we're actually going to just go in general first, just with general values for the battery voltage and resistor values and capacitor values, because one, that's going to be just a lot easier in terms of the math and not having to write down numbers constantly and calculate things all the time. And two, it'll give us a general result, and then we can plug in later. So we have our battery voltage minus the potential difference across this capacitor minus the potential difference across this one down to 0, because the negative terminal of the battery is said to be 0. Now, remember that the definition of capacitance is charge per unit voltage, so C equals Q over delta V. So that means that delta V is equal to Q over C. So each of these potential differences, which we're just calling V, is equal to that charge divided by that capacitance. So we're going to plug that in here. Now, we really don't care about these charges on these capacitors at this point. We do care about the currents, though. So what we're going to do is we're going to take a derivative of this equation with respect to time. And when we do that, every Q is replaced by an I. And every constant is replaced by 0, because the derivative of a constant with respect to time is 0. Remember, this E is just the battery's EMF, so to speak, the battery voltage. So now this gives us a relationship between the current that goes into this capacitor compared with the current going through here. In fact, it's kind of, there's a negative there. So I4 is equal to negative C4 over C3, or this is C4 and this is C3. So now, using the junction rule, we realize that, okay, the current going into this junction, coming out of the battery, in other words, is equal to I1 plus I3. And oh, by the way, that's the same current that's going back into the battery over here. That's equal to I2 plus I4. So apparently, I1 plus I3 is equal to I2 plus I4. Next, we're going to use another Kirchhoff loop rule around this upper right part and realize that, okay, this is a positive terminal right here, this is a negative terminal down here, so we're going to have a positive V3 going this way minus I1 R1, where this 8.8 ohm resistor is R1, and then just come back over here is 0. Remember, Kirchhoff's loop rule works around any loop that you can think of, including useful ones like this one right here. So this gives us another equation. And you might think, okay, I'm going to take a derivative with respect to time of this equation. Well, actually, no, I'm not. We're going to save this for later. going to do the same thing around the lower right box. So right here, I'm just summarizing what we've obtained so far. We have an equation for the current, I1. We also have an equation for I4. So now that we've summarized our results so far and also isolated for I1, we're going to do a loop rule around this lower right one. Same loop rule as before. We're going to go counterclockwise, starting from the positive terminal right here. Actually, really from the negative terminal, but we have a voltage gain, this V4, so to speak, which again is just Q4 over C4, minus I2R2. So that's what we have right here. So that allows us to solve for the current right here. It's equal to whatever this charge is divided by R2C4. So now we can combine these results with what we had right here from our junction rule. So we're going to plug in our result for I1, we're going to plug in our result for I2, and that gives us this result right here. And we're also going to plug in what we got for this current 4 from before as a result of the fact that we need to have just going back to this slide right here, that from our big overall loop rule just from the two capacitors there. So we're going to plug that in. Now remember that equation that we differentiated with respect to time? Well, that equation itself is also useful because that's where those charges are. We can plug in for those charges and get rid of them. So when we do that, this is our result. So we're going to isolate for our charge Q4 using that original equation from this big overall loop rule. So when we do that, we're going to move this Q4 over C4 over to the other side over here, and then we're going to multiply both sides by C4. So that's where this C4E comes from, and also where we get a C4 in the numerator right here. So now that we have done that, we can plug this in right up here, because remember, this equation right here, this was our junction rule equation. We plugged in our I1 right here. We plugged in our I2 right here. We plugged in our I4 down here. All that's left is I3. Everything right now is in terms of that charge I3. So now we simply needed to get rid of this Q4, because after we get rid of Q4, then everything will be in terms of I3 and Q3. So we use our original big loop equation to isolate for Q4, get rid of it, and now we plug in. Everything that's left in this in terms of things that can change is all the same thing that can change. It's what's going on with this capacitor right here. So we have the current going into it related to the charge that it actually has. That's very important because now we can actually get something that is quite meaningful, as you'll soon see, because effectively this is just going to turn into an algebra party. What we really want to do is isolate for this E right here, this EMF, and see what that tells us. So at this point, it really is just an algebra party. If you wanted to, you could really just outsource this to your 8th grade brother or sister or friend or something like that and pay them $5 to finish it off for you while you attend to something that's more important with your time. But anyway, for those of you interested, here's how that goes. This is where we were in the last step over there. So the next step right here, we need to add this Q3 over R1 R3 to R1 C3 to both sides, because again we are trying to isolate for this. So we do that, and when we do that over here, this is where that ends up turning out. After that, we're going to multiply both sides by R2C4. That's where that ends up in the numerator over here as well as over here, and what's left on the right side is this numerator over here. So now we're going to add a C4 over C3 to both sides, and what's left is this C4E right here, and then divide both sides by C4. Well, what happens when we do that? This C4 right here goes away, this C4 right here goes away, this C4 right here goes away. A C4 cancels in each term, and now this battery voltage E is by itself. So now, notice there's a Q3 right here and a Q3 right there. Oh, we can just factor that out. So what do we have here? We have E equals stuff times I3 plus Q3 over stuff. I went from this step to this step because remember the potential difference across a capacitor is charge per unit capacitance, so to speak, because capacitance is charge per unit voltage. So this is just a simple equation effectively with a resistor in series with a capacitor. Well, sorry, in parallel with the capacitor, because you kind of add the stuff up. But this is an easy equation to see what's going on with. We have our effective resistance, or equivalent resistance. We have our equivalent capacitance right here. So, from that, since we have our R and we have our C, we can get a single equation for the time constant. We multiply the R and the C together. And there we go. And we can do a little simplifying, turn this 1 into a C3 over C3 just so that we get a common denominator and we can cancel out these C3s. So we just get a C3 plus C4, or just, for that matter, just multiply it through. You get a C3 right there, and that cancels out that C3. So however you want to think of it, this is our time constant. And even though we were asked to get a specific time constant, I consider this derivation important enough that I decided to put a box around this equation right there. Don't memorize it, but it's still an important equation for this particular type of problem. So now we actually are ready to plug in some numbers. But first, something to note. You might wonder, is like, well, wait a second. We were hinted at in part E that there might be time constants. Well, what would it be? Because here we were dealing with everything going into capacitor 3. What about everything going into capacitor 4? Well, it should be apparent, and it is true, that we would have obtained exactly the same result if earlier on we had eliminated variables and tried to solve for I4 instead of I3 and C4 instead of C3. Because, look, just exchange capacitors 3 and 4 and exchange resistors 1 and 2. Or don't. Either way, you get the same result. Exchanging capacitors 3 and 4, well, this whole thing is commutative right here. This is commutative, and this is commutative. So whether or not you exchange your resistors, or whether or not you exchange your capacitors, or you do both, you're going to get the same value for the time constant. You might get different values for the currents, but we weren't asked about the currents. We were asked about the time constant. So now, we're ready to plug the numbers in. And when you plug the numbers in, you get a time constant of 2.5 microseconds for this equation. So hopefully this solution to a rather difficult RC circuits problem helped to reinforce a lot of the concepts having to do with RC circuits, even though you probably will not be dealing with something that's this difficult on a test or an AP exam. Thank you.